Understanding cell and molecular biology requires some basic chemistry. In this video, I'll talk about electron shells or orbitals. Consider a nucleus that has just one proton and one neutron, proton plus charge. That will attract an electron, and that electron will spend most of its time in a defined space around the nucleus. What I've drawn here is a hydrogen. Let's add one more proton and neutron here. That'll attract another electron. These two electrons balance the charge perfectly, and there's enough space for them, even though they repel each other, to fit in this region. What if we add a third proton and neutron? That'll attract another electron, but it can't fit in this space where these two electrons already exist. So it has to go in the space around the outside. What if we add one more positive charge and a neutron? Well, that'll bring in another electron in this outer space. I'm starting to define electron orbitals here with this innermost one, the 1s, and this one being called 2s. Chemists need names for them, so 1s for a sphere, 2s also a sphere. What happens if we add another positive charge? That will attract another electron, and this one now fits into an orbital with a different shape. This one fits into an orbital that's the shape of an ellipse. It will spend its time mostly in this ellipse, about 90% of its time. I'll come back in a moment to why it's that shape. Let's add one more. Again, we'll draw in another electron, and it will be in another one of these pear-shaped p orbitals. And one more. Now I need to go above and below the plane here. I'm going to do this with dashed lines. That means it's not in this plane, it's coming up toward you. And we add another electron. What if we add one more? We'll pull in another electron, but now we're going to match this p orbital on the other side, and this electron will spend its time mostly in that space. We add one more positive charge, another electron, and it's spending its time in this space. And finally, one more. Now, remember, this dashed line orbital went up. Now I have to go down, and we bring in another electron, and that's down underneath. So now I want to talk about the shape of these orbitals. These shapes are defined by where the electron spends most of its time. And they take this shape because the electrons are attracted to the middle but repelled by the electrons that are already there. They can get close some of the time when these electrons happen to be further away. And they're bounded on the edges because there are nearby electrons that are repelling them. And so these electrons are not spending that much time in this middle area because there's a nearby electron that would be repelling it. This p orbital goes above and below, and finally the 2s is filling the spaces between all these other orbitals. These electrons are fitting in between. This turns out to be a very stable arrangement of electrons. I'm going to redraw it to make that point about stability. Here's our innermost shell, the 1s, the 2s, one of those p orbitals, another one, another p orbital, another p orbital, and then one coming out and one going under. So here's the innermost orbital. Here's one of the p orbitals. Here's another p orbital with a pair of electrons, and finally the s2. So we have s1, s2, p, another p, and another pair of the p orbitals. We have 2 electrons in each set for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are often drawn in what's called the Bohr Model, in which the 1s orbital is shown with 2 electrons filling it, and the octet of the 2s and the 3 sets of p orbitals are shown like this, with each of these circles representing a pair of electrons. This would be the s1. One of these, any of them, is s2, p, p, and p for the 3 p orbitals. Most of the elements that are involved in biological molecules are either this size or they have one additional shell with another set of 8 electrons. As I mentioned, this structure is very stable. The electrons are balanced by their repulsion, mutual repulsion of each other, and their attraction to the center. If we tried to add one more proton, then that will attract another electron, but that electron cannot fit inside the boundaries I've already drawn. The electrons that are already there would repel it too strongly, and so it's forced to be the first electron in this next ring. A problem with being the first electron in that next ring is it's not held in place very well. It's very easy for it to move around anywhere in that ring, and that makes it not a very stable electron. It's relatively easy for that electron to be lost, and we're going to talk about that a bit when we talk about sodium, which has 11 protons, the one I've just drawn here. Sodium loses an electron really easily to become a positively charged ion in water. In the next video, I'll talk more about covalent bonding.